project. So don't worry. After I post it, I will give you 1 month to complete it. Okay? Yeah. Starting from the post time, 1 month. Yeah. But another thing related to this project, remember our midterm. So here, I need to remind you the midterm at this time. March the 16th, right? Based on our syllabus. March 16th, that time. Yeah. So I want to set a deadline of project after the midterm. Yeah. Because before the midterm, I need to let you focus on the midterm, right? Yeah. So the due deadline for the project 1 should be after the midterm. Okay? Yeah. So here you can see, 1 month, this week sometime I need to assign, 1 month. And this month we know only 28 days, right? Oh, no, 29. 29 days? 24, so 29 days. Yeah, 1 more day, yeah. But I need to count at least 30 day, 31, at least 1 month to complete that project, okay? All right. Yeah, but it should be after the midterm, the deadline. Yeah. All right. So that information, let you know. Yeah. All right. The topic, part C, asymptotic notations. The most abstract part of this class. Yeah, this topic, most abstract. Yeah. Last time, growth function, are a little abstract. Yeah. But here, more abstract. Yeah. After that, then we won't have very abstract topics. Okay? Yeah. One thing, so after last class, one student asked me some question about, remember last time I did some proof using the L'Hopital's rule, that's calculus 2, right? So one student asked me, for this class, the requirements for calculus 2. Yeah, here, let me explain that. Calculus 2, yeah. We do not require calculus 2, so do not worry too much. Yeah. I know many students, they do not have a calculus 2, okay? Yeah. The reason, because for the department, we changed the requirement, yeah, several years ago. Long time ago, we require calculus 2, okay? Yeah, long time, 10-something years ago, we require calculus 2. Yeah. But later, because many students, they have trouble to pass calculus 2, so later, we remove that, calculus 2. So for that reason, large portion of the students, they do not have the calculus 2. Okay? Yeah. So for this class, I won't give you any question using calculus 2. Okay? Yeah. Here, the L'Hopital's rule only used to prove some results. Okay? Yeah. When I prove, I have to use L'Hopital's rule. Okay? So you just try your best to understand. If not, you just take the result. Okay? Yeah. Whatever the result I write it out, you just take it and use those results. Okay? Yeah. So you do not need to do the same thing. Okay? Yeah. So the questions I ask you in the homework assignments tests based on the results. Okay? The one result here, let me use an example. Last time I said exponential functions dominate polynomials. That result. You just use it. When you see exponential function with base number a greater than 1, you know it increases much faster than any polynomial. You only need to know that result. That's enough. Okay? You do not need to prove it. Okay? The proof, I did it in class. I use L'Hopital's rule to prove it in class. Okay? You just use it. Yeah. So that's all you need. Okay? Yeah. So that's my answer about calculus 2. Okay? Other than that, we won't have any topic using calculus 2. Okay? Only this place. Yeah. Yeah. All right. C.1, Introduction to Asymptotic Notations. This part, although abstract, but we have to learn this topic well, because for algorithm, later you will see we will use asymptotic notations all the time, everywhere. Okay? So it's a very important topic. Yeah. All right. Yeah, so when we start, let's look at the limits of two growth functions. So now, after last class, now you know what we are doing here. Okay? Yeah, but here I do some summary. Yeah. Limits, when we take limits of two growth functions, yeah, because we want to compare their growth functions, which one faster, which one slower. Yeah. So we take limit of the ratio of two growth functions. Yeah. When we use the limit to compare two growth functions, we have these cases. Here I list all possible cases. Yeah. 4 cases. Basically, we have these 4 cases. The first case, 0. The limit is 0. Yeah, so it's possible. Yeah. The second, it's a constant C. C, you can treat it as non-zero constant C. Non-zero constant C. All right? Yeah. Third one, infinity. Infinity. Then, the last one, 4. Other, yeah, here, there is one. Sometimes people call does not exist. Does not exist. The limit does not exist. That's possible. Yeah. Yeah. Think about the limit does not exist. Okay? Yeah. Think about the fluctuation. Okay? The limit. Because if a limit exists, it converges to some number, right? If limit exists, it converges to some number. Yeah. Yeah. Or infinity. Infinity is another special case. Infinity, we do not treat as it converges to any number, but it goes to infinity. So there is a special definition describing the limit is infinity. Okay? Going very large, yeah, infinity. Okay? All right. But there is one, the limit does not go infinity. Okay? Yeah. The limit does not go infinity. Yeah. Fluctuation, think about if the ratio takes the value, yeah, let's say 1, 2, 1, 2 in this pattern forever, we cannot say the limit exists, right? Because it does not converge. No specific number, the sequence converges, right? You cannot find any number the sequence converges. Yeah. You know, right? Yeah. So that's our case number 4. We say the limit does not exist. Okay? Yeah. So that's all the cases when we take the ratio of two growth functions, yeah, and the limit. Yeah. Case 1, yeah, let's look at case 1 first. Yeah. Case 1, the limit equals 0, you can see the denominator is much larger than the numerator, yeah, because the ratio becomes 0. When n is very large, the ratio approaches to 0. You can say the denominator dominates the numerator. Yeah. So in that case, we call the order of growth of f of n is less than order of growth of g of n. Here we use the concept, order of growth concept. Yeah. So what's that order of growth? I explain it later. Yeah. There is some order order of growth. Yeah. That concept. Yeah. Yeah. We compare order of growth of these two functions. So we know denominator has higher order of growth, yeah, for case 1. Case 2, non-zero constant, we say they have the same order of growth. Constant, okay? Yeah. Yeah. Here, actually, because when we talk about growth functions, these two functions should be positive. Yeah. Remember, these two functions represent the number of basic operations. That number should be positive. Yeah. So we don't worry about the negative number. So the C should be positive number. Okay? Positive constant. Positive constant. Yeah. All right. Case 3, infinity. So you know, this time, order of growth of f of n is greater than order of growth of g of n. Yeah. Yeah. Numerator dominates the denominator this time. Yeah. So you can see, it's very easy to see which one higher, lower for the order of growth concept. Yeah. All right. Case 4, the limit does not exist. Then it's hard to, yeah, because a lot of things could happen. Yeah. Yeah. Okay. Yeah. So this time, we cannot look at the limit. It does not exist. So in this case, case 4, you need to look at other method. The limit method does not work in this case. Yeah. So you need to choose a non-limit method to compare two growth functions. Yeah. So we can find one non-limit method to do the comparison. Okay? Yeah? All right. Yeah. Here, before I introduce some compact notation. Yeah, so that's related to our asymptotic notations. Before I introduce that, let me explain this order of growth a little bit. Yeah. Yeah. So you want to get a better idea on this concept, order of growth. Yeah. All right. Here, let me first use simple examples to show you the order of growth. Yeah. All right. When we have simple function like this one, the first one, that's wrong. Yeah. All right, look at this function, n square function, okay? Yeah. N square function, it's a monomial. Yeah. There is a order for this monomial. Yeah. There is order concept for this monomial. Okay? Yeah. 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 Order, we know polynomial has an order concept. Yeah. Polynomial has a degree concept. Polynomial has an order concept. Okay? Yeah. Yeah. But here, when we talk about order of growth, yeah, because this order, that's the growth order. Okay? Yeah. That's the growth order. So we do not say, polynomial order, growth order, okay? It's a different concept. Yeah. Here, when we say order of growth for this simple function, we can use this exponent number to the order of growth, yeah? Because that number directly reflects how fast this function grows. Yeah, that's an easy way, yeah, all right. Then, so you can see n to the dth power function, d, so, this d can be used as the order of growth. Simple, right? Yeah? Yeah. So for power function, order of growth is very easy. Yeah. Yeah. But the hard part is, for other complicated functions, the order growth is hard to describe because there are some other functions. It's hard to use the simple way to describe the order of growth. For example, one example, 2 to the nth. Okay? It's an exponential function. Okay? We know its order of growth is very high, but it's hard to use a number to represent it, how high it is. We know higher than any of that d. Okay? Higher than any of that d. But we cannot find any particular number to describe the order of growth. We can only do comparison. But there is no specific number that can be used for the order of growth in this situation. Okay? So that's one example. Another example, it's hard to use specific number to describe, that is the log n. Log n. Look at that. Okay? So we know it increases slower than the power function. Power function increases faster than the log function. But it's hard to use a specific number to describe the order of growth of log n. Okay? So for that reason, it's hard to give you, very clear definition for this concept. You just feel about it. Okay? So the concept here, how to clearly describe it. You just feel about using examples to feel about this concept. All right, so that's the order of growth. Okay? You can treat it as a hidden concept. This concept, how to see it directly, it's a hidden concept. But for power function, you can see it clearly. Okay? Power function. But for non-power function, it's hard to see it. It's hidden. Completely hidden. Okay, non-power function. Okay. All right. Next, compact notation. Case 1, this time, because if we do not use compact notation, case 1, we need to say a lot of words to describe case 1. So that's not efficient. So people like to use concise notation, to describe the situation of case 1. Here we use asymptotic notation. This is our first asymptotic notation. Okay? So in this case, case 1 case, we say f function, f of m, belongs to little o. Our first asymptotic notation is little o notation. Little o of g function. G, the growth function, relatively simple growth function we want to use to give us idea for another growth function, f of n. That's the role of g of n. G of n usually simple, so we know how fast it grows, g function. But f function usually more complicated. So hard to see how fast it grows, so we use it to compare with the g function and see which one faster, which one slower. Here, because the limit equals 0, we just use little o to tell us that information. Because it's short, it's simple. In our discussion, if we use this simple, concise notation, then it's very convenient. That's the reason we use asymptotic notations. Little o, okay? So not 0, it's o, here. Similarly, for case 2, we use little theta. Yeah. Little theta. Yeah, Greek alphabet theta. Little theta. F of n belongs to little theta of g of n. That means same category, yeah, because f and g, yeah, their growth order the same, so we can treat them in the same category. Yeah. But here we use theta. Yeah. Yeah. You may ask why people use theta. No reason. Just some early mathematician used that first. So later people follow. Okay? Yeah. 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 Because some notation there is no reason, like a pi. Yeah. Why people use pi to represent some special constant, right? Yeah. Some early mathematician, yeah, so use that pi. Okay? So later, so everyone, yeah, all use that pi. Okay? E notation. Yeah. All those. There is a history, okay, early history. So here, little theta. All right. Case 3, f of n belongs to little omega. Yes, our third asymptotic, little omega. It means the limit goes to infinity. Okay? F of n over g of n. That limit goes to infinity. So here, little omega. Yeah. Yeah. Later, yeah, this is here the first 3 asymptotic notations. Yeah. Later you will see another 3, little o, then big O notation. We use more. Okay? Yeah. Most of the time, actually, we use big O notation. So next few slides, you will see big O notation. Yeah. Then little theta, big theta notation. There is a big theta notation. Yeah, quite different from little theta notation. Big theta. Okay? Yeah. And a big omega notation. Yeah. Right. Yeah, sorry. Actually, this is big theta, right? Can you recognize? Yeah. Little theta similar, yeah, but just smaller. Yeah. But this one, this one is a big theta, not little theta. Okay? Yeah. 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 Little theta, we won't use it. Yeah. We just use big theta. Yeah. Because I see it not that big, so I call little theta. So actually, yeah, big theta we write this way. Theta inside, yeah. So we use, some special way. So little theta we use this way. So they're different. Okay? So here it's a big theta notation. Yeah. 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 All right. So little theta we won't use it. Okay? We won't use it. Yeah. It has some special meaning, but we won't use it. Okay? All right. Yeah. So then the big omega, little omega, then big omega we use it sometimes, yeah, but not too much. Yeah, sometimes. Yeah. Big O we use a lot. Big theta we use second most. Yeah. Big O we use the most. Big theta we use second most. Okay? Yeah. Then all other notations we do not use much. Okay? Yeah. But here, I just let you know these notations. Yeah. Yeah. Later, it's not hard. We just use big O and a big theta. So, yeah. Yeah. Very easy to get used to these 2 notations. All right. Case 4, yeah. You can see the limited way does not work well for case 4. So we need a new method for case 4, non-limit method to study case 4. Yeah. There is one, yeah, for case 4. Yeah. All right, so what's that? using upper bounds and lower bounds. No limit. We use inequalities. Upper bounds, lower bounds, we can compare two functions. Which one grows faster, slower? So another important way, inequality way. So you have limited way, inequality way. Okay? Sometimes limited way is better, sometimes inequality way is better. Okay? Yeah, all right. Objective. Yeah. Even if the limit f of n, g of n does not exist, even if, all right, yeah, we can still compare their growth functions, or these two growth functions. We can also compare by using inequalities. Yeah. All right. How to do it? Yeah. The function g of n, usually a simple function like n squared, n log n, usually. Yeah. So if not like these, still okay. Okay? Still okay. It's still legal. Yeah. All right. Yeah. The function f of n could be a complex function. Yeah. All right. Use some constant multiple of g function to approximate f of function. Yeah. Yeah. Simple. Yeah. How do we do the comparison? We know constant multiple, that constant. Because when we use different constant multiple of g of n, we use the function in the same category, right? Yeah. If two functions, they have the same order of growth, then we treat them in the same category. Yeah. Here, constant multiple, that means we use functions from same category of g to do upper bound of f of n, or lower bound of f of n. If we can get information, upper bound, lower bound, then we can say something, right? Yeah, we can say something about comparison between these two growth functions. Yeah, all right. Specifically, can we find two positive constants, C1 and C2, such that C2 constant multiple, so positive constant, be sure, they are positive constant. Yeah. C2 times g function less than or equal to f function less than or equal to C1 times g function. One is lower bound, another is upper bound. If you can find such inequality, these two inequalities, one upper bound, one lower bound, conclusion, you can have some conclusion. What's the conclusion? You can say f and g, they have the same order of growth. The reason is simple, because g has the same order of growth with C2 times g of n, right? G also has the same order of growth with C1 times g of n. And the f of n is between these two functions that have same order of growth with g function. That's why we say f has the same order of growth of g function. That logic, okay? Upper bound, lower bound, that logic. Yeah. All right, yeah. So you can see, here, if we compare this inequality method with our previous limit method, you can see even if the limit does not exist, this method can still work. Can still work. Yeah. Can you imagine that situation? The limit does not work, but this method works. Okay? Yeah. 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 Let me give you a simple example here. Okay? Let me give you a simple example. Yeah. All right. The limit does not work. The limit does not work. Yeah. But the inequality works. Okay? Let you see it. Yeah. Otherwise, you cannot imagine how that could happen, right? It's hard to imagine. Yeah. Here, the example is very simple. Okay? All right. So let's consider the limit here. Yeah. Let me make a special f function and a g function. So let you see, the limit does not work. Okay? Yeah, the fraction. Let me write this way. All right. Parenthesis. 4 plus -1 to the nth times n squared plus 1. That is the f function. How about that? F function. Okay? G function. All right. 3 minus -1 to the n function. N minus 2. How about that? This function. Can you see if its limit exists or not? Yeah, look at that. Yeah, because here, n squared plus 1, n squared minus 2, plus 1 minus 2, very small, we can ignore, right? When we take limit, we can ignore, okay? So n squared, basically these two terms can be canceled out. Yeah. When n very large, they're almost the same. Yeah, slightly different, but we can cancel out. Yeah. After cancel out, yeah, so that means after simplification, we get this limit. This time, 4 numerator plus -1 to the n, and 3 minus -1 to the nth. Can you see if its limit exists or not? Can you see it? Yeah. Because we just consider n even and odd, right? Yeah. So we can see, the fraction number when n is even or not odd. Okay. All right. When n is even, let's say even first. So the numerator 4 plus 1, that's 5, right? Even denominator 3 minus 1, that's 2. So 5 over 2. When n is odd, right? Numerator 4 minus 1, odd. Okay. So it's 3. When n is odd, denominator 3 minus -1, 3 plus 1 is 4. Okay? Yeah. Then next round, this pattern repeat. Yeah. Next round, 5 over 2, 3 over 4, alternatively forever. Yeah. Is there any limit? No limit. Okay? Yeah. Fluctuation up and down, but never converges. The ratio never converges. No limit. No limit. Think about that. Okay? Yeah. Yeah. So if you want to use limit way to compare these two growth functions, you would fail. Okay? Yeah. You would fail. Yeah. But if you use our new this inequality way, it would work, right? Yeah. It would work. You can find C1, C2. Yeah. Yeah. You can find C1, C2. Yeah. 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 Here, actually, I didn't put an important condition. When we talk about this inequality, there is a condition. So that is where n greater or equal to some constant n0. Yeah. So this inequality only needs to be true where n greater or equal to certain constant 0. So we added this condition so we can make the whole thing more rigorous. I will explain this. This condition important. Although it's simple, but it is important. So we can make the whole discussion more rigorous. Yeah. Okay? Yeah. All right. Yeah. So that's our understanding using inequality method, upper bound, lower bound, to compare two growth functions. Okay? Yeah. All right. Next topic, C.2, define asymptotic notations. So this time, we need to write rigorous definitions for asymptotic notations. Yeah. So let me, write a formal description, then explain. So what's the meaning? Yeah. Try to understand. Yeah. It's very abstract. Yeah. But we need good understanding. Yeah. All right. First, big O notation. Yeah. Our most commonly used asymptotic notation. It's called a big O notation. Okay? All right. Formal definition. Yeah. What's that? For a given function g of n, the notation big O of g of n represent the set of functions. So I think you know the meaning of set of functions, right? Yeah. A set of functions. Set of objects. Here the objects are functions. So a set of functions, f of n, yeah. F of n you can treat as a general representation of some element in this function, okay? Yeah. That satisfy the following condition. Yeah. Yeah. All the elements in this set should satisfy the following condition. So what condition? Inequality condition. There exists some positive constant c. Here, only one constant. Because here we only look at one of the bounds, not two bounds. One of the two bounds. Yeah. Constant c and some non-negative integer n0. Yeah. So remember the previous slide, I added the n little n0. Yeah. We need it. Here, in the formal definition, we need this condition, yeah, such that f of n less than or equal to c multiple of g of n, c times g function, when for all n greater or equal to n0. Okay? Yeah. For n less than n0, we don't care. Which one larger, which one small, it's not important. Yeah. When n less than n0, n0 is a constant. It must be fixed. n0 constant must be fixed. Okay? Yeah. You can choose, you have freedom to choose that little constant, n0, but as soon as you choose it, then you fix it. Yeah. So when you change different n, this number must be fixed. Yeah. All right? Yeah. That's the formal definition. Yeah. Here you can see we only have upper bound, c times g of n. We don't have the lower bound. Yeah. So that means for big O, you only look at the upper bound. You do not look at the lower bound. Yeah. Because you feel that's good enough. We only need the upper bound. That's good enough. Okay? That's the big O notation. Yeah. most popular asymptotic notation, this big O. Okay? Yeah. All right. Later, I will explain why. What is the role of N0? Okay? You may wonder, what's the role of this little N0? Right? Its role is important. Yeah. So I will explain. Yeah. I will explain. Yeah. When you have a little more understanding, I will explain. Yeah. Yeah. This time, probably a little earlier. Yeah. So we need to get more information before we come back to this topic. Okay? Yeah. All right. N0. Yeah. All right. Yeah. But yeah, here you see this N0 explicitly. Yeah. Yeah. But sometimes people want to hide that N0. Yes. Another way, when people write this formal definition, people like to hide this N0 notation. But the meaning is the same. Just people use a different wording, some vague wording. People use some relatively vague wording to hide this N0 notation, symbol. Now, what's that? People say, so here, so the way to handle it, but how to hide it? People do not mention that N0 constant, okay? To hide it, people say this way, where N is sufficiently large. When you see this sentence, when you see this half sentence, okay? When N is sufficiently large. What's the meaning N sufficiently large? It means this N0 wording, okay? Yeah. You just go back to this N0 wording. That's the same meaning as this where N is sufficiently large. Because sufficiently large, it's a vague meaning, right? Wording. Very vague. Yeah. How large is sufficiently large? Right? For different people, their answer could be different, right? Sufficiently large. You say sufficient large, but some other people, they feel not sufficiently large. Okay? Yeah. But here, why people take this vague wording? Because people can handle it well. For one particular question, sufficiently large or not, given a problem, then people knows when it is sufficiently large. Okay? Yeah. If a general problem, then nobody knows how large is sufficiently large, right? Because it's too general. Okay? Yeah. But for specific problem, for example, for sorting, okay? Sorting problem, then people know, what number is sufficiently large? Okay, things like that. For concrete problem, specific, concrete, real-world problems, you know how large is sufficiently large. Just select some N0 constant. After N0 constant, this inequality always true. You know, you find the one. Draw the line, okay? After this line, sufficiently large. Before this line, not sufficiently large. Yeah. So that's the meaning. Okay? All right. Yeah. So here, let me give you the graph for this definition. Yeah. So the graph here, you can see, our goal, we want to describe this f function. That's our goal. Okay? G function is known. G function is a simple known function. So we can use it to measure f function. Okay? To measure f function. Yeah. How to measure? We multiply a constant to this g function. When you multiply it, so you can raise the G graph up and down. Okay? Sometimes you lower down the graph, sometimes you raise it up. Okay? Yeah. When you choose certain appropriate constant C, you check if its graph is completely above f function, complete above, but there is a vertical line, this dotted, dashed vertical line at n0 location. Yeah. You can choose that line. Okay? Before that line, doesn't matter. Yeah. Which one larger, which one smaller, it's not important. Okay? F function could be larger, C times G could be smaller, but it's not important. Yeah. Why not important? Yeah, here, let me explain a little. Because if n less than n0, that means the problem size is relatively small. Okay? Relatively small size. When the problem size is relatively small, then our computer is so powerful, we don't worry about the, performance. Okay? Yeah. Our, the typical computer is so fast. So we do not feel it's a problem handling relatively small data size computing problems. We don't worry about it. Our main concern is when n is very large after the dashed line. Okay? Yeah, that's our concern. Yeah. 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 Very far away from this vertical line. That's our concern. Okay? Yeah. 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 So that's the reason the specific n0 number actually is not that important. Yeah. Yeah. Just somewhere. Okay? Yeah. Somewhere. Yeah. But after this line, inequality holds. Yeah. You need that. Yeah. You can move this vertical line. Okay? Move this bar. Yeah. But yeah, to some place, certain place. Okay? Yeah. All right. Yeah. But when you apply the inequality, you need to fix the location of that line. Okay? Yeah. When you want to check if this inequality holds or not, then you cannot move. Okay? Yeah. You need to fix it. Yeah. Because if you move, you get trouble checking if inequality holds or not. Okay? Yeah. So at that time, you need to fix it. All right. Yeah. Okay, yeah. So that's the big old notation, the formal definition. Yeah. Later, for other definitions, similar. Yeah. We only need to change the inequality part. The remaining sentences are almost the same. Yeah. So let's look at the big omega notation. Yeah. Upper bound, previous one, here, lower bound. Yeah. Same wording. So you see, almost the same wording. Yeah. We only change, the only place you change, lower bound. C times G function, you use it to be a lower bound of F function. Yeah. Because lower bound is not unique. F function can have many lower bound, not unique. Yeah. So here we only need one lower bound in the form of C multiple of G function. The n part. You need to find some n0. Yeah. Yeah. So from the graph, this time C multiple of G function is below the graph of F function after passing that dashed n0 line. Before it, not important. Doesn't matter, not important. Okay? All right. Then, the last one, formal definition. Yeah. So that should be enough. Our last formal definition of asymptotic notation. This time, big theta. Just combine the previous two cases, one upper bound, one lower bound, putting together, you get this big theta notation. Okay? The same wording, yeah, is same word. You need to modify, some small places. Yeah. Not this time, C1, C2, two constant, upper bound, lower bound. Okay. Yeah. All right, and N0, then inequality, both upper bound and the lower bound. Then also N sufficiently large, N greater or equal to this N0 line. Yeah. Okay? Yeah. Yeah. From the graph, you see, one upper bound, one lower bound. Okay? Yeah. So this way you can see you describe F function in a nice way. Yeah? Both upper bound, lower bound, same category. This time you can say same category, right? Yeah. The previous two cases, yeah, you cannot say they are in the same category. Yeah. Because one end still not fixed, right? One end you can change a lot. The lower bound. Yeah. For big O notation, the lower bound side, you can change a lot. You cannot control the lower bound side. For the big omega case, you cannot control the upper bound side. That can change a lot. Yeah. And then this one, both sides pretty much there. You do not have much freedom to change. Upper bound side, lower bound side, same category. Now you can say they are in the same category. Okay, yeah, big theta. Yeah. Yeah. All right, so that's the formal definition of these asymptotic notations. Yeah. So because after we give the formal definitions later, we do not need to use so many words to write their meaning. Okay? Yeah. We just use some short, this short asymptotic notation expression to describe their relationship based on the order of growth relationship for their order of growth information. Underlying meaning, we know, all these definitions, the underlying meaning, it's there. Yeah. Yeah. We do not need to speak that out. Yeah. Okay? Yeah. A lot of meaning there. Yeah. All right. Yeah. Okay, so that's the C.2. Yeah. Yeah. All right. Then, C.3, examples of asymptotic notations. Yeah. Yeah. We need to use these notations to compare some growth functions. Yeah. Here, I show you examples, part 1, part 2. Today, part 1. Yeah. Next time, another half, part 2. Okay? Yeah. Several examples. Yeah. These examples, after I show you, I need to calculate the limits using L'Hopital's rule. Yeah, L'Hopital's rule. Yeah, yeah. But after the calculation, you just use the result directly. Okay. Yeah. So the result of these examples. Yeah, because in your homework questions, homework 1. I will give you several such questions. Okay? Compare growth functions. Yeah. You do not need to do L'Hopital's rule. You just use the results here. Okay? Yeah. All right. First one, example 2.1. Yeah. Show that n plus 2 belongs to big theta of n. We have two ways to show it. We have two ways to show it. One way, limit way. Okay? Limit way. Simple. Second way, definition way. We have formal definition for big theta notation. So we can use that definition. Here. Limit way is so simple. Limit way, I can do it immediately. Let's take the limit. So here, very easy to click the button. You calculate this limit, n over 2, f function over g function. Right? Yeah? We can calculate this way. Numerator, denominator, we divide it by n. So numerator becomes 1 plus 2 over n. Denominator becomes 1. Okay? Now, when n goes to infinity, 1 plus 2 over n goes to 0, right? N is very large, extremely large. The limit 2 over n becomes 0. The limit is 0. Okay? So 1 plus 0, 1. 1 over 1 is 1. Answer, the limit answer is 1. So because the limit is 1, here, let me write it. Limit is 1. So 1 is the non-zero. It's a positive constant, right? Positive constant, we know the ratio limit positive constant, they are in the same category, so that's big theta. Big theta. Okay? Same category, both upper bound, lower bound. Here we didn't use upper bound, lower bound, but in the same category. Okay? All right. Here, let me use the definition. The limit way is so simple. Let me run the definition here. When you need to prove it by the definition, you need to find upper bound, lower bound of g function, constant multiple of g function, to be upper bound, lower bound of this f function. F is n plus 2. So let's look at the lower bound. Lower bound, n plus 2, always greater than n, right? N is a constant multiple of g, 1 times g function. G is n, but here we use 1 times n. We drop that 2, okay? Plus 2. We drop that constant plus 2, so the value becomes smaller, so that's the lower bound. Lower bound n0, we want to see n0, which line, after which line? Greater or equal to 0. Because our n cannot be negative, right? N means our problem size. Problem size cannot be the negative number. So we use n greater or equal to 0. That's the lower bound. Then upper bound. This time we need to look at upper bound. For the upper bound, can we use some constant multiple of n, g function n, that is greater than n plus 2 expression, f function? Yeah? So, because there are two terms here. N term itself is a constant multiple, right? One constant multiple of n. How about that 2? Can we enlarge that 2 number to make it a constant multiple of n? We can change that 2 number to make the function value larger. Okay? Here, how to change? How about we change 2? Here the constant is C2 equals 1. How about we change 2 to n to make it larger? we are very generous. We change 2 to n. Yeah. The reason, because we want to use constant multiple of n. So here we change 2 to another constant multiple of n, 1 constant multiple of n. But there is a condition. If you make this change, you have a condition. N must be greater than or equal to 2. Yeah. So this is our n0. This is our n0. Okay? Yeah. Now you can see sometimes we need to use that n0 number. Okay? Yeah. So we have the upper bound, 2n, n plus n, 2n. Okay? Yeah. So for upper bound, we need to use n greater or equal to 2. Lower bound, we only need n greater than 0. Yeah. But we need both. We need both true, so we take n greater or equal to 2. That will make both true. Yeah. Yeah. Both sides, the inequalities hold with this condition, n greater or equal to 2. Both sides true. Okay? Yeah. All right. So the C1 equals 2, C2 equals 1. And you also find N0. N0 is 2. So you complete the definition. The definition tells us we need to find these 3 numbers, N0, C1, C2. So you complete the proof. Yeah. All right. Let me do another proof. 2.2. This time, n cubed belongs to big omega of n squared. Big omega, we know lower bound. You only need to find a constant multiple of g function n squared. Yeah. Yeah, but here, we know n cubed greater or equal to n squared, yeah, because they are positive integers, right? Yeah. Or if you include 0, 0 fine, they are the same. If you include n greater or equal to 0, but n is an integer number. N refers to the problem size. Problem size number. So it must be integer. So then we know n cubed always greater or equal to n squared. When n equals 0 or 1, they are equal. After that, n cubed always greater than n squared. After that. Because we only use integers. Yeah? Yeah. So then we can say, because lower bound, c equals 1, right, this time. C equals 1. Yeah. N0 equals 0. Yeah. So by the definition of big omega, so we have the conclusion. Okay? We have the conclusion. Yeah. Yeah. All right. Yeah. Yeah. After this one, yeah, so let's do one more example. 5 minutes. Yeah, one more example. This example, n plus 2 parenthesis cube, this function belongs to theta of n cubed. Not hard, but many students, yeah, I saw their way to do it very complicated. Yeah. The way is not good. Yeah, so I will show you their way. Yeah. All right. So when we start, we want to find, yeah, although here you can use limit way, similar to the one in the previous page, we can use limit. Find the limit equals 0, so we can get a conclusion. Yeah. But here, let us practice the definition. Upper bound, lower bound. Okay. All right. n plus 2 this time is cube. Yeah. How do you deal with cube? Yeah. Lower bound is easy. We know n plus 2 always greater than n. Yeah. and this n non-negative. Yeah. So when you raise to certain power, still the inequality holds. Yeah. All right. N greater equal to 0. Yeah. Same as before. Yeah. Then the upper bound, we can still use our previous way. Yeah. Here, we know n plus 2 less than or equal to n plus n when n greater or equal to 0. Yeah. So then, inside the parenthesis, we get a 2n. 2n greater than n plus 2. Yeah. Then we take cube both sides. So that cube function, yeah. Here we also have our n0 equals 2. Yeah. So our cube function, we can take both sides. So we get an n plus 2 parenthesis cube less than or equal to 2n parenthesis cube. That's 8n cube. 8n cube. Yeah. Yeah. So you have both upper bound, lower bound. Yeah. This way, pretty easy. Yeah. But here I like to point it out. Some of the students, they didn't do the right way. So they do it in a very messy way. Yeah. Try to avoid this messy way. So what's their messy way? They expand n plus 2 cube to a polynomial. Yeah. So that's in this way. Equals n cubed plus 3 times 2, that's 6n squared, plus 3 times 2 squared, that's 12. Yeah. 12n plus 2 cubed, that's 8. So they expand it out like that. Because after the expansion, it becomes harder to work on, right? Harder to work. Yeah. Then, although you can still find upper bound, but much harder than before, right? Yeah. So do not you do it in this way. Yeah. Because later, I give you raised to 5th power, right? Yeah. Some question I raised to 5th power. If you do expansion, it becomes harder and harder. So don't do expansion. Yeah. After you get inequality, then you take the, exponential operation. Okay? Yeah. Yeah. All right. So let's stop right here. So I have one question left for part 1. After we finish the last example, so next time, then I show you a few, important examples. Yeah. These are just simple examples. Try to get you better understanding on the concepts, definitions. Next time, we need some important results. Okay? Yeah. Regarding your homework assignments. Yeah. If you understand well, you can solve several homework questions. Yeah. All right, so that's